On behalf of the Moyal Medal Committee that consisted of Professor Ursula de Marco, Professor Sun Duong, Associate Professor Georgi Sofronov and myself, welcome to the 2021 lecture and virtual presentation of the 2021 Moyal Medal to distinguished Professor Louise Ryan from the School of Mathematical and Physical Sciences at the University of Technology, Sydney. My name is Samuel Muller, and I'm the head of the Department of Maths and Stats here at Macquarie University. A special welcome also to Professor Magnus Neiden, who is to my right, the Executive Dean of the Faculty of Science and Engineering, who makes up 50% of the in-person audience. Before we continue our proceedings, I would like to acknowledge the traditional owners of the Macquarie University, the Wallamatical clan of the Darug Nation, whose cultures and customs have nurtured and continue to nurture this land since the Dreamtime. I also acknowledge the traditional owners and people of the land from which you join this online meeting. We pay our respects to elders past, present. We thank Christine Hale, our department manager, and Haley Prescott, my executive assistant, for organizing today's event so well. Let me now turn to Jose Ochoa Moyal, whose achievements and legacy we continuously celebrate through the Moyal Medal. Joe Moyal was one of Australia's most remarkable scientists. His insight into the interaction between mathematics, physics, and statistics led him to make contributions to these disciplines, which have had far-reaching ramifications in all three fields. The Moyal formalism, which he introduced in 1949, is being developed today in physics as the Moyal quantum mechanics. Born and raised in Palestine under the British Mandate in 1910, he went to France to study and then work in electrical engineering. He moved to Cambridge to study mathematics and then returned to Paris to study statistics and theoretical physics. His academic career started after the Second World War as a mathematical physicist in Belfast and then as a statistician in Manchester. At this time, he made fundamental contributions to both fields, introducing the Moyal bracket into physics and developing the foundations of stochastic processes. Moyal came to Australia in 1958 and worked for 6 years in the Department of Statistics at the ANU in Canberra, there making fundamental contributions to the theory of population processes, enabling researchers to track population size as well as the characteristics of individuals. He extended this work at the Argonne National Laboratory near Chicago, where he worked from 1964 to 1973 on the peaceful uses of nuclear energy. He returned to Australia to spend the next 5 years as a professor of mathematics here at Macquarie University. Following his retirement, he went back to Canberra, where he maintained his interest in the fundamental questions of science. The recipient of the Moyal Medal will have made distinguished contributions to research in mathematics, physics, or statistics. It is awarded annually on a rotating basis in these disciplines. Let me now turn to this year's Moyal medalist, and please, Louise, feel welcome to join me here so that we can see you. We are particularly proud that you, Louise, have completed your undergraduate degree here in statistics and mathematics at Macquarie University. As a Macquarie alumnus, you then left Australia in 1979 to pursue your PhD in statistics at Harvard University in the United States. A few years later, in 1983, Louise then took up a postdoc in biostats in Harvard and was promoted to assistant professor in 1985, eventually becoming Henry Pickering Walcott Professor and Chair of the Department of Biostats at Harvard. Louise then returned to Australia in early 2009, where she took up the role as Chief of CSIRO's Division of Mathematics, Informatics and Statistics. In 2012, Louise then joined UTS as a Distinguished Professor of Statistics. You are renowned for your methodological contributions to statistical methods for cancer and environmental health research. Louise loves the challenge and satisfaction of multidisciplinary collaboration, and the many of us who know her, she is one of the most wonderful collaborators there are. Louise has received numerous prestigious awards, including her 2012 election to the Australian Academy of Science a 2015 honorary doctorate from Kent University, Harvard's 2015 Centennial Medal, and having been a most outstanding president of the International Biometric Society in 2018 and 2019. And I learned an awful lot just observing how Louise champions statistics, biometrics, but also diversity in this wonderful field. She has now over 30,000 Google citation, and her H index is just short of 100. Louise, this Moyal Medal is in recognition of your outstanding contributions to statistics, especially wide and deep contributions in applied statistics, biostatistics, and methodological work for cancer and environmental health research. The committee particularly appreciated that you are an exemplary citizen who has demonstrated tremendous leadership on an international and national scale. You have and are making a difference to hundreds, if not thousands, of statistics and biometrics researchers from diverse backgrounds. I now have the honor to invite our Dean, Magnus Snyder, Professor Magnus Snyder, to award the Moyal Medal.
Thank you, Samuel.
Thank you, Sam. And Louisa, I know I'm taking liberties here, but I wanted to say just a few words extra in addition to handing over the award.
Okay.
We all approach scientific disciplines from different perspectives, and I read up on you. My thinking went to, as it sometimes does, or quite often does, to a 2011 Nobel laureate in in literature, by a person by the name of Thomas Tranströmer, a Swedish guy that I happen to know because I'm Swedish. His most famous poem, if I translate it into English, reads something like, "Two truths approach one another. One comes from within, the other one comes from the outside, and where they meet, you have a chance to see yourself." To me, that is profound because it speaks to the human nature, because as a follow-on effect, it is important to understand that when it comes to decision-making, which is one of my favorite research fields, not my personal one, but that I like to read up on and understand more, because I think it is important for the human race moving forward. So when I read up on you, that's some of the things that I read and saw, and I just find it fascinating. So thank you to Samuel for inviting me here today.
Thank you.
Thank you for the opportunity, because what I will then formally do is to thank you for, on behalf of the Moyal family, present this award to you, which is the 2021 Moyal Award for Outstanding Achievements in the area of statistics. Many warm congratulations.
Thank you so much.
Thank you so much.
Thank you so much. Thank you, Samuel. Thank you. Just the medal so everybody to see. So I'm very, very touched. I have been very fortunate in my career, and I've been humbled to receive a few awards along the way, but the Moyal Medal really stands out for me in a very special way. It has stirred up a lot of memories, and it's given me a beautiful sense of coming full circle since I started my academic career here at Macquarie 46 years ago, 1975. It's really hard to believe. I'm very touched that several of my professors and colleagues from those days are here today, and after the presentation, we're going to have a great time catching up over lunch. But before I get to my technical presentation, I can't resist a little bit of reminiscing, and I hope you'll all indulge me. So again, there's a medal. Thank you very much. I'll share my screen for my presentation. So originally, I started out in Macquarie's actuarial program. At that time, Macquarie was the only university in Australia that offered actuarial studies. But after a while, I wasn't feeling quite so happy in the program. Maybe it's because I was the only girl in a class of very nerdy guys, and you can see 4 of them down in the bottom left-hand corner here. Maybe it was discovering that actually I didn't really like finance all that much, or wasn't very good at it. But I think what it really was discovering that as part of the actuarial program, we took some really great courses in statistics and probability. And I soon realized that this is what really got me excited. I have vivid memories of taking Maths Stats 1 from Anne Eland. This would be back in 1976. And I was mesmerized by the beauty and elegance of the subject. Macquarie was doing other innovative things as well at that time. I recall heated debates with Pam Shaw and others about the special programs they were offering at that time for mature age students. Pam was convinced that it was reasonable that people would not know what a negative number was. I was convinced that they would. And so we're trying to decide, and we decided that we'd all go home and we'd call our mothers and ask our mothers if they knew what a negative number was. Yes, this was the 70s, and I'm afraid it was still a little bit sexist in that way. When I called Mum and asked if she knew what a negative number was, she said, "Oh, yes." And I felt vindicated. But then she added, "I don't remember much about them, except I know that when you add two of them together, you get a positive." So I'm afraid Pam did win that argument after all. The Macquarie Stats Group was, and still is in fact, vibrant and strong, with some really excellent lecturers who really knew how to engage students. Thinking of people like John Croucher, Eddie Oliver, Ben Zenworth, Malcolm Hudson. I remember how excited everybody felt by the prospect that Don McNeil would be joining the department after a stint at Princeton in the US. Indeed, Don brought a lot of vitality. This is a picture of Don at the upper left-hand corner, teaching intro stats back in the days. And you can see people are falling out of the aisles to attend his lecture. The 70s were an exciting time for statistics. And I remember Don leading some great seminar groups talking about cutting edge developments like the bootstrap. Don was a great influence on me, not only then, but also over the years. I'm very sorry that because of COVID, today's event has to be online, but a silver lining for me is that several of my family are joining online, including Jonathan, Ronnie, Jenny, and Bede. I'm really grateful. I, of course, wish my mum and dad were still around to enjoy this moment with me. I remember them, sorry, I told my sister I would not cry, but I remember them driving up from Bega for my graduation and being very proud of having a daughter who had a university degree. Anyway, enough reminiscing for now. I'll turn to my technical presentation. There we go. So what I'll be talking about is a project that I've actually been working on for the last several years. And this has been with a postdoc of mine, Stephanie Clark from UTS, and also two colleagues, Rob Heinemann from Monash University and Dan Pagenden from the CSIRO. Water is an increasingly precious resource all over the world. And according to Geoscience Australia, Australia is the driest continent besides Antarctica, apparently, in terms of average annual rainfall. Many parts of Australia rely on access to groundwater, and water extraction licenses are valuable, tradable, and if you listen to the news, often highly political and contentious. So for this reason, good quality monitoring systems, quality modeling, and effective forecasting are really essential so that we can plan for our future. So let me start with a really, really quick review of classic approaches to groundwater modeling. So the classic approach is very much based on physical models, requires data, knowledge, assumptions about the shape and structure of the underground area, the nature of the aquifers and so on. You need information about rainfall, information about how the system is recharged, extraction patterns and so on. So it's quite complicated. The models themselves are complex systems of differential equations, require numerical solution that are typically slow to run and subject to a lot of uncertainty. So in the last decade or so, there's been a lot of growing interest in more data-driven approaches using statistical modeling and machine learning. It's interesting, Water New South Wales, I'm so impressed. They have the most amazing repository of information about water resources across the state. If there are any students out there who are looking for good sources of data, this is the place to go. It's really absolutely astonishing. What our focus today is going to be on looking at bore water levels. And I've got a couple of photos here that show some of the technology that's used to measure those levels. Some of the bores in the network have been measured as long back as 40 years ago. These days, some of them are equipped with automatic telemeters that capture real-time data. But in the old days, it would require somebody to go out and manually use an instrument to measure the level. And basically what the measurement tells you is the measurement from the top of the pipe down to the water level, as shown in the diagram over to the right. Now, modeling bore water levels is challenging. And you can see here, this is the levels in a bore over a 10-year period or so. This is in middle southwestern New South Wales, the Murray area. You can see here, and it's fairly typical, lots of pattern and variation in the patterns. And you can imagine here there might be very cyclical demand as over the season and demand for irrigation and so on. Occasionally you get some really funky patterns where nobody really knows what happened, but anyway, it is a challenge. As you think about how you might go around about doing this modeling, it's natural to think of technology called time series modeling, which has been developed for data that are indexed in time. There are many, many variations on this. Classic, Box-Jenkins, ARMA, AFIMA, ARIMA, and so on. The class of models, the broad class that we've been interested in is what's called dynamic regression modeling, where you're able to incorporate additional predictors and you have an autocorrelated error term built in. You can also do things like, it's a little bit of a more straightforward way in some ways, you can just build an explicit lag into your model. So if you want to predict the water level at time t, well, you use the water level at time t-1 as a starting point. And then also, recent years, people have become interested in these things called recurrent neural network models, which have been developed in the machine learning world. But choosing the best strategy is hard. And part of what I want to talk about today is that some of the compare and contrast, there's lots of trade-offs and there will be lots of subtle differences and lots of dualities. Also, deciding the best option for a short-term prediction can be quite different than for a long-term prediction. So my presentation today is basically taking you through our journey, exploring these kinds of techniques and coming up with a couple of recommendations and thoughts for the future. So our first efforts took place in the Alstonville Plateau, which is up in the northeastern part of New South Wales. It's an area where there's lots of rain, fair number of telemetered bores, no particular problems with missing data, and it's no really large-scale temporal patterns that we had to take account of. These are some of the predictors that we looked at. So on the top, you've got the rainfall, and you can see there's a few days there where there's massive rainfall events. The middle one in the green shows evapotranspiration, which is thought to be quite a strong predictor. And on the bottom is the bore water level, which is what we're trying to predict. So let me jump to the bottom line and then back off and tell you a little bit about how we got there. So this particular slide shows the results we got from two seemingly quite different methods. The top one is a classic time series method called an ARIMA, we built in lots of lagged climate variables, lagged values of rain, evapotranspiration, and so on. The one on the bottom is what's called an LSTM, or a long short-term memory recurrent neural network model, which is becoming very popular and has shown a lot of promise for predicting all sorts of things, largely developed originally in the context of natural language processing. I'm going to take a real brief aside just to tell you how these work, and then we'll come back to discussing them more. So the dynamic regression modeling via ARIMA, basically the idea here is that you predict the outcome that you're trying to predict, y, as a linear function of predictors, your x's, plus an error term, which can have some time series structure in it, autocorrelation structure. You can generalize these models. So this is really fairly familiar. You can generalize if you want, you can build interactions into the model, you can build nonlinearities, but you have to do that manually. You have to create the predictors yourself. The neural network models really are a simple generalization, conceptually simple generalization of this idea. the concept is that you're still trying to predict the outcome at time t. You've still got your predictors, the x's in the blue circles here. But what they do is they create an intermediate layer which can basically construct new predictors from the input predictors. And this is the layer where you can start to create things like interactions, nonlinearities, and so on. A key element is what they call these activation functions. And this is the component of the neural network that allows the introduction of nonlinearities. You can, when people often talk about deep learning, and what that one interpretation of that is, it's the same kind of thing, but you're just adding in extra layers. So sometimes people will call these a feed-forward network, or maybe a multi-layer perceptron. In theory, you can add in lag values as part of your predictor space, but the problem is that the network can become unstable. So what people have done is tried to look at more computationally effective ways of doing that. And here's one of the earlier networks. I think this one was developed in the 90s. It's called the Elman network. And the idea here is that when you're trying to predict the outcome at time t, in addition to the predictors at time t, you also use the values of the hidden nodes at previous time points. So that's how you get the time lag built in. It's a very simple one, this one. The one that we're using is what's called this LSTM, or long short-term memory model. And the idea is that in addition to having that structure where you've got predictors, lag values of the nodes and so on, it also carries along this set of memory cells that's in the purple here. And the idea is that as the network's progressing through in time, it might see something and it might say, hey, I think that might be important. I'm going to remember that and hold on to it. So in the case of modeling our bore water levels, it might be something like, oh, there's a flood, there's standing water. I need to keep track of that and hold that as part of my prediction for later. Like I said, this technology is being used widely in natural language processing and sentiment analysis. And that's a setting where the context is really important. So it's able to capture the context through these memory cells. So just getting back again, it's quite remarkable that on the surface, that the two technologies, the classic time series and the LSTM, they're really quite different. Yet when it came to prediction, they did remarkably similarly, at least in this bore in Alstonville. And you can see here, remember the dark blue is the bore water level. That's what we're trying to predict. The turquoise is the rain. The green is the evapotranspiration. And the orange, or the brown, whatever color it is, that's the prediction. You can see that the two predictions, they're not exactly the same, but they are remarkably similar. And remarkable, really, how well they're able to capture some of those nuances of what's going on. And this is a paper that we published last year that describes some of these results. So the results, they're definitely promising, but there's some pros and cons, which I'll just quickly touch on now before we elaborate a little bit further. The ARIMA, it's got a lot of appeal, but you have to come up with a parsimonious set of predictors. So you need your subject matter experts involved. Now, to me, that's not a problem. I like subject matter experts, but it's something where you have to do a lot of a priori work to identify the right set of predictors. You can include interactions and nonlinearities, but you have to manually construct them. You do have to be careful because it can destabilize if you've got too many predictors. On the other hand, the LSTM and the neural network methodologies, they have this ability to construct the rich set of predictors themselves. So basically, it lets the computer do a lot of that construction. I've just gotten a strange message here. Something about somebody's requested live transcription. I don't know what that is, but I'll enable it. So, okay, it's enabled, whatever it is. The LSTM uses a very different fitting technology. It's not maximum likelihood in this quite the same way that we're used to in statistics. It is a bit prone to overfitting, so you need a bit of a different technology, and it needs large sample sizes, and it needs a lot of model tuning. To me, the big disadvantage of the neural networks is that they're a bit black boxy. It's hard to say what's driving the prediction. Okay. So let's switch over now to the Nemoy Basin. Nemoy is in northwestern New South Wales on the opposite side of the Great Dividing Range, and it is a much harder problem. The models are much harder to get a good prediction. It's a much drier area. There's a lot of groundwater extraction because it's heavily farmed agricultural area, and there's also a lot of mining. So it's just a complicated system. There's also a lot of regulation of the water through dam releases, weir releases, and so on. And the data actually were much more sporadic. This visualization on the bottom shows that we only have just a small handful of bores, that's in the yellow, where we had daily data. And most of them were quite sporadic measurements going back to the 70s, almost as long as my career. The biggest challenge with the Nemoy was that there was massive variability from bore to bore. And you can see here, this is just a selection of 20 of the bores, very, very different. And it probably just depended on where they were and what was going on in terms of extractions. So I'm going to tell you about a few of the things that we tried. None of them are perfect, but at least it gives us some direction for next steps. So we started out doing some neural network methods for single bore analysis, pulling in the richer predictor set, which I think is over on the side. It's being hidden by, no, it's not. Yeah, there it is. Pulling in the richer set of predictors, the rainfall, the evapotranspiration. We included surface flow now because we knew that we had this phenomenon of the dam releases. So that was important. And we also had the extractions data. I'll come back to that later on because there's a few little issues with that. We did have to add in, to get a good fit, we had to add in some additional time variables, day within year and overall time to get a good fit. But the results, they're not perfect, but they're pretty good. So on the top is the prediction for one of the bores, and you can see this really odd pattern where back in the 70s and 80s, it was fairly steady and not a lot of variation. But then starting in the 90s, and then particularly since the 2000s, you get these really massive dips every year. To me, that has to be extraction. So interestingly, what we were able to do was we were able to say, well, what would it have looked like if we hadn't had any extraction? So we set all the extractions to 0, and you can see the turquoise line here still got a bit of fluctuation in it because I don't actually think we're measuring extractions all that well. But you can see that explains away those funny dips later on. So that was quite promising. When we applied this to all of the telemetered bores in the Nemoy region, we did a pretty good job of fitting them. But the big problem was that we only could use it on the telemetered bores, and there's a lot more bores we couldn't use. And also, you can't use these models to predict in the future. So what the department would really like to do is to say, well, what might these bores look like in 30 years' time if we have, a decade of really low rainfall? They really want to get at the more of the understanding, underlying nature of what's happening so that you can predict into the future. These models are great at describing the patterns and to some extent understanding what's going on, but you can't use them to predict into the future. So what we wanted to do was to turn to models that allowed us to take account of all of the bores at the same time to see if that could make more sense of things. So we used what I'm using the royal we here. This was Stephanie's work. Stephanie had experience using these things called self-organizing maps. It's a type of unsupervised neural network, and it basically is a nice way of clustering complicated data. It's not using any of the predictors, but it's just trying to cluster and make sense of things. So she applied the technique to all of the several hundred bores that we had access to, and she found that they grouped into 16 different clusters. And you can see here the clusters on the right. Some of the clusters seem to be just doing a fairly general, a lot of them actually seeing a fairly general decline over time. A couple are more stable. There's actually one, the bottom left-hand corner, for some reason seems to be increasing. Who knows what's going on with that one? So this was a good exploratory technique. And we'll come back to it in the sense that when we show you some of the other results from things that we've worked on, we use our groupings here to help display the results. So it's quite interesting to use it. The first thing we tried was fitting the LSTMs to the cluster-specific curves that we got from Stephanie's self-organizing map. And you can see here that the gray is the actual predicted curve for that cluster, and the red is our prediction. And again, it's not perfect by any means, but seems to do a pretty decent job of capturing the ups and downs, the general ups and downs. Recall again, just the LSTM, it's a type of neural network. The nice thing about it is it's able to carry along these, what they call memory states, which allows it to say, look, I think something's happened, which might be, I'll keep track of it and it'll help me with my future prediction. So it's thought to be a good methodology when you've got both short-term and long-term patterns that you're trying to capture. We then, once we looked at the LSTM fitted to the cluster, we then wanted to ask the question, well, how's it doing for individual bores in that cluster? And you can see there's a lot of variation within the individual bores, lots of variation. Again, probably things like people starting to extract from that bore. You can see over on the right-hand side, it's doing a pretty good job, although not perfect, with predicting the individual bores. Now, I want to use this as a segue to a topic called global modeling, because this is an example, in a way, of a fairly newly emerging technique called global modeling. It's becoming increasingly popular in time series analysis. And the idea is that if you're trying to predict a group of time series, then your average prediction errors can be better on average with one simple flexible model that's assumed to apply to all of the series, rather than going in and individually optimizing each of the separate series. I suspect that some of the statisticians around will say that can't be possible, but I'll show you a couple of graphs in a minute that suggest that actually in certain circumstances, it can actually work quite well. So how would the global model concept work in our setting? Well, to show you that, I'll first of all show you how it might look if we do just a global simple neural network, leaving out the memory cells part. So the idea here is that you create one gigantic stacked data set that includes all of the data from all of the bores. You just put it all together into one giant spreadsheet, but you have to include another variable that says, what bore did this one come from? So you can see here in the spreadsheet, you've got the date of the collection, the bore, the name of the bore, what the water level was. Now, interestingly, you can also then just throw in your lags. So I've got the lag at time 1 lag back, 2 lags back, and so on. Same thing with the rain. You can put your rain in at the same day and then lag at 1, 2, and so on. So once you've done that, then you can just fit one gigantic model that can include the bore ID as a predictor. So the neural network can basically use that to help predict if it needs to. So we'll come back to it. It can do a pretty good job at single-step prediction, as you can imagine, but it can't go into the future, again, because it needs a lag. So it doesn't have them. It's got them for one step, but that's all. So it wasn't helpful for the future prediction. But there's a new technology that really has just been published in the last couple of years, developed by the guys at Amazon, not my favorite company in the world, but obviously they do a lot of market research trying to understand the patterns of sales of their products. And they've developed this technology called Deep AR. And the idea is that it takes the neural network concept. They're using an LSTM structure again with the memory cells in there. But the thing that's a little bit different is that they also include lagged outcomes as predictors. And what they're doing is this global model concept of fitting one gigantic model to all of the time series together. And the other nice thing about it is that like the more statistical approach, and it is a bit more of a statistical approach. It does give prediction intervals, so you can get a little bit of a sense of the uncertainty in your prediction. When I first was reading about deep AR, I thought this doesn't make sense at all. You know, how are they taking into account the different bores? Well, it turns out they're not really. It's this global model concept. So I'll come back to that presently, but let me just first show you how it worked for the Nemoy. And what I've got at the top is the results of fitting the global model via deep AR to all of the 231 bores. You have to specify what's called a context length. And what this means, it's actually quite important, but what this means is that when the model is constructing those memory cells and looking back at how far back it's going to go to include its lags and all of that sort of thing, that's quite an important parameter. So in this case, we specified a context length of 5 years. You also need to tell it how far you're trying to predict into the future. I'm showing you here the results for 5-year prediction. And what we've done here, we've used Stephanie's clusters again, just to plot the results. So one of the things, we didn't use the clusters when we were fitting this model at all. So it's actually quite remarkable in a way that when you plot the results by the clusters, you can see that the results are very tightly bound up with the clusters. So they seem to be it's doing a good job of recreating that or capturing that information that's in the clusters. So the top panel on the right shows all of the data going back to the 70s with the black curves at the end showing the prediction. So the colored dots are the actual bore measurements and the black is the prediction. Down the bottom panel is a zero in on the prediction area. And you can see that, again, it's not perfect. It's not perfect prediction, but we're statisticians. We don't expect perfection. It's okay. But you can see that they do a pretty decent job of capturing some of the fluctuations that we see in the bore levels. I would argue that it's doing a better job earlier on in that 5-year prediction interval, but we'll come back to that. It's also doing a better job in some clusters than others, and we'll come back to that as well. So just a few thoughts about it. One small point, I really just wanted to show this because I thought it's such a nice visualization. Stephanie's got a real talent at visualization. This is just a visualization showing that before we ran deep AR, it was really important to standardize all the variables to a mean 0 standard deviation 1. When we didn't do that, the results were really bad. So if you ever want to run deep AR, make sure you standardize your variables first. The second thought is that I really do feel that, and it makes sense, that extractions are very important. If you're going to predict the bore levels, you need to know what people are taking out. But we're pretty sure that, at least at this stage, I don't have time to go into a lot more detail about it, but it's pretty clear that the extractions data are not fantastic. The quality is not quite what we need. The extraction's not measured on a continual basis, but it's annualized. And what you really would like is to have nice quality, continuous monitoring of the extraction levels for all of the bores, the same way that we've got the continuous telemeter modeling for the water levels. So that's something for the future and something we've fed back to the department as part of our recommendations. But one of the things I did want to take a couple of minutes to talk about was this idea about context length and also prediction intervals. Now, as I mentioned to you, we picked a context length of 5 years, but we were curious what would happen, how the results would compare if we chose different context lengths. So you can see here a visualization of how well we did predicting in one of the clusters when we had a 6-month, 12-month, 24-month, 36, 48, or 60-month context length. Right immediately below that shows the mean square error, which is a measure of how accurately our predictions are going. But you can see it down the bottom, that when your context length is not long enough, it just is not able to do the kind of predictions that you need. So what we found was that you needed at least 48 months, and we found that 5 years or 60 months worked particularly well. I just want to take a brief aside to show you a figure from this paper by Montero Manso and Rob Heinemann. Rob Heinemann's one of our collaborators on our project. And Rob and his colleague recently published this paper in the International Journal of Forecasting. It's an astonishing paper if you get a chance to go and read it. And what they showed was that if you're trying to predict a suite of time series, so maybe it's like you're predicting the time series of sales of products in your company, or you're predicting electricity usage in a lot of different towns or counties in Australia or whatever, that you can do one of two things. You can go in and individually analyze each separate time series. You can do a REMA, ETS, really fine tuning it to get the best possible prediction for that particular time series. Or you can do a gigantic model where what they did in this graph, believe it or not, they just said, okay, we're trying to predict this outcome and we're going to throw in lagged outcomes as predictors. For each series, it gets its lags thrown in as a predictor. And what this figure shows is that so long as you have enough lags, and Rob, they're showing here that you need, maybe if you get up to 24 or 25 lags, you can outperform the models that are created by really fine tuning the individual models fitted to individual series. So it's quite a naive model. This is just linear regression with lots and lots of lags thrown in. It's quite astounding. But this is the same phenomenon that we're seeing with deep AR, which is just in a neural network context. So it's quite amazing. So we then sort of asked the question, well, what if we wanted to predict out to 10 years? Because like I said to you, what the department would really like to do is say, well, what happens if we get 10 years, 20 years of drought? What's going to happen to our bore levels? How far into the future can we predict? So we tried using deep AR to predict into the future. And as you can see, I've got on the left-hand panels the 5-year prediction, which I showed you already, which was okay, not fantastic, but okay. On the right, we've got the 10-year, and it's terrible. So you just can't predict that far into the future, which to me makes sense. The deep AR, this kind of technology, is really good for shortish term predictions. And I did a little computer simulation, which I think I've got enough time to just quickly show you. I just wanted to really explore this. So I generated 2,000 data points from a very naive linear model with a predictor, X. I made a predictor that looked like some rainfall. I had a time trend and a time interaction. So in my figures here to the right, the blue dots are the data that I generated. So then what I did, I took the first 200 points, so 10%, to fit a model. I did 3 models, the linear model, the correct model, a naive linear model with just lag Y thrown in as a predictor, and then a more sophisticated ARIMA model. Then I evaluated the predictions, and I did it 2 ways. First of all, I just predicted the next 200. So I'd call that like a shortish term prediction. And that's the middle panel on the right-hand side. And you can see from that figure that all 3 methods are doing fairly similarly, particularly at the beginning. You then start to see the ARIMA and the lagged model starting to lose it a little bit, lose the plot, nice pun intended there. The bottom, I'm predicting the very last 300 time points. So I consider that like a prediction into the future. And what you can see there is that the linear model, the correct model, does perfectly well. But the ARIMA and the lagged model, they just can't do it because you don't have the lagged data that you need. So it just can't predict into the future. So to me, that's exactly what's going on with these global AR type models. They're fantastic for shortish term prediction. But if you want to predict into the more far future, you really need predictors and features that can help you understand. So just a few concluding remarks. Time series models, particularly some of these recurrent neural network models like the LSTMs, show a lot of promise. They need a lot of data to do well. But these days, we seem to be getting better and better at collecting data in pretty much every domain. And it's particularly the case in the water domain. And I showed you that Water New South Wales site where there's these richly telemetered monitoring and extraction bores all over the state. It's only going to get better. And also, I think as people realize the potential of these more empirical data-driven approaches, they'll realize the importance of having the accurate, reliable data, and people will collect more data. So it's going to happen. It's still early days, which kind of makes it exciting. In the Alstonville area, you saw that we could actually do a really quite good job using these methods of predicting. And I would feel quite comfortable there starting to predict into the future what happens under different climate change scenarios, rainfall scenarios, and that kind of thing. Regions like the Nemoy are a lot more complicated because it's such a heavily extracted area. You've got a lot of industry, the mining industry, coal seam gas, you've got a lot of agriculture, irrigation, and so on. So it's an area where there's a lot of demand. At this stage, the extraction data is not measured well enough for us to properly build it into the models. So you can't actually ask those questions of what's going to happen into the future. But so going into the future, we can do a good job predicting over the next year or two. But if you really want to predict more longer term, you have to make the effort and invest in getting these other things measured. I also think we didn't do it just because it was a bit beyond the scope of our project, but there's a potential to extend these models to not just look at a single catchment as we've been doing, but to do a multi-catchment model. And you could look at the whole of New South Wales. That then opens up possibilities of using other information. For example, remote sensing data can tell you about land use. And there's actually some pretty cool remote sensing technologies that can even tell you how much water is sort of in the system and that kind of thing. So this potential to expand it out to much larger models obviously would be a lot more computationally intense and so on, but there's a lot of potential there for doing that. There's lots of methodologically interesting things that you could explore with these kinds of models. And to me, one of the things I've loved about this project, and I've been working on this project about, it's coming up for 2 years now, it's like my perfect project because it's very data rich. You need statistics, you need modeling to try to make sense of lots and lots of messy data. But it's important. You're tackling a problem where the answer has impact. And so it's that perfect sweet spot of work for a statistician where you can play with lots of nice mathematics and statistics, yet you feel you're contributing something helpful to society. And you get lots of great ideas for more technical methodological papers that you could work on with your colleagues and so on. So I think I'll stop there. Thank you very much for listening. I really appreciate it. And again, I'm just so grateful to be the recipient of this year's Moyal Medal. Thank you very much.
Thank you very much, Louise, for a most stimulating presentation and taking us on a journey starting in Bega, where your parents drove up to Macquarie University to the northeast and then to the northwest of New South Wales. I don't know if you've intended it, but you certainly covered New South Wales exceptionally well.
I did intend it.
We have a couple of minutes to take questions, and I invite anyone in the virtual audience to ask a question or make a comment. And you can either raise your hand and I can call you.
Yes.
Let me see you raise the hand.
David Keith.
Hi, David.
Yes, David, we can hear you.
You have to unmute, David.
I did, and then the host muted me.
Oh,
so
sorry.
Thank you for a very interesting talk. Your models look like they might be good enough to use them in a different way, which is to potentially report on or evaluate where the extraction data is in error. It's not consistent with the observed data. Is that a possible option? And then maybe, for example, detection of fraudulent reporting of extraction of data?
Oh, wow. That's that's quite a politically loaded comment there. But look, I think you actually could. I think it's got a lot of potential to do something like that. But what you would need is to have some sources of data where you had reliable monitoring, so that you could say, what would it look like if I've got reliable monitoring data? So you can train your models to recognize what it should look like. And then you can go in and you can say, look, there's something funny going on with this boar. It's not matching with our predictions. But you would need to have sources of information where you could be confident that you were capturing the predictions properly. Right now, we just don't know. We just don't have enough data. But potentially, you're absolutely right about that. Good question. Thank you.
Thank you.
Another question?
Richard.
You have to unmute, Richard.
Hello.
Hi.
Thanks for the very interesting talk.
Thank you.
I just had a quick question. So at the end, you said these LSTM models turn out not to be very good once you move to a longer time scale, like 10 years rather than 5 years. So I don't know very much about these things, but from my limited understanding, I have heard that that's one of the limitations of these LSTM architecture, that it kind of doesn't perform very well over long periods of time. I just wondered if you're investigating other architectures. I mean, the natural language people are into this transformer architecture these days.
Yeah. Well, let me just make one comment on that. It's not the LSTM that's a problem. The LSTM can actually do a fabulous job, but it needs the predictors. What's not good for predicting into the future is this particular version, what they call deep AR, which is LSTM with the AR structure built in. It's my feeling is, and Rob Hyman, I've talked about this with Rob Hyman, who's like, one of the world's experts in forecasting, and he agrees with me that for long-term prediction, you need features and predictors. You can then put those into an LSTM. What's not good is the LSTM trying to utilize the lag structure to help you predict. So, and then so I hope that makes sense. But with regard to your other question, there's always new technologies emerging. And I have to say, I wouldn't consider myself an expert on all of these, but it's definitely worth keeping up with the literature and seeing if there's other exciting technologies emerging. I would love to see some fusion of the statistical way of thinking with the LSTM type technologies. For example, building hierarchical Bayesian strategies that can properly account for boar-to-boar variation whilst having like a common central LSTM type framework. I think there's massive potential with that. It's beyond my pay scale right now to develop something like that. It would be computationally really, really intense. But I think that there's stuff like that I think will start to happen more and more. There's so much more that needs to get done.
So we can go to you, Nan, first, and then I go to the room that is staffed by Haley.
Thank you so much for this very interesting talk. Yeah, actually, my question has something to do with this kind of mixture of a more classical statistical method and more like latest machine learning method. So yeah, as you mentioned, so there will be advantages for both methods. And my question is, in general, is that possible to combine these two and to utilize the advantage of both methods? And in particular, say in this kind of a neural network, can we turn some nonlinear part into a linear part?
Yeah, I do think it is possible. And I think that it's interesting that I think the potential for that interface between classical statistics and machine learning is very exciting. But for people to operate in that particular space, you need to be computationally pretty sophisticated. And I guess, like, certainly statisticians of my generation, we didn't have enough computer science to be able to do the tools that you'd need to be able to implement those methodologies. But potentially, you really could. To me, the nice thing about the neural network type structure, they really are just like the kind of models that statisticians like to use. It's just that they have this feature in there of engineering additional interactions, nonlinearities, and so on. But those are then included in the model in a linear way. So it's actually quite familiar. That I've read some of the stuff by Brad Efron, Trevor Hastie, Rob Tibshani, and so on. And they go back to some of the projection pursuit methodologies which were being explored back in the 70s. I remember Don used to give us lectures about projection pursuit. It's a generalization of that concept. So I think the potential to do that fusion with classical statistics is great.
Yes,
So
thanks.
into the room, and this will be our last question, and then we wrap up at our end.
Oh, it's me for the last question. Thanks, Louise, for the talk. Nice talk. It's Benoit. I don't know if it's a typo or not, but it raised me a question. In your data, you show at one time 2 different observations at the same time. So maybe just one day, I think it was a 30, I don't remember the month, and after two observations same time. I don't know how you deal with this, and if in your experience, what do you recommend if we have irregular space-time observation?
Yes, wow. Yes, wow. Couple of things. Oh, sorry, I'm getting an echo.
For the last question, it's something harder.
Yeah, I'm getting an echo. I'll try to ignore it. When we did the deep AR, yes, we did have multiple measurements on the same day. That was the whole point, because we were fusing information from multiple different time series. The classic LSTM, if I understand correctly, requires single points observations measured on successive days. And again, I mean, when I say LSTM, the methodology itself can potentially have gaps in the data and so on. But it's a question of how do you actually fit it. We were using a package called Keras in R, and that required that there be no missing data and that you have 1 observation per time point. So it's really a question of, if you have the facility to do all the programming yourself, then yes, there's ways around things like missing data and handling multiple observations per time point. But if you're using the available packages, then they may not allow it. So it's a question of, do you use an existing package which has got other advantages, or do you try to program it yourself so you can take care of those sorts of nuances? There's definitely an issue for our data.
Please let me join in thanking Louise again for a most wonderful Moyal Medal presentation and a stimulating discussion.
Thank you. Thank you very much, everybody, for coming. I really appreciate it.
So this brings us to the end of the online part of the Moyal Medal. We will now celebrate Louise together with a number of friends and partners in crime across the road in a restaurant. Thanks also to our executive team, Magnus Meiden, for having been here for this celebration today. And just to the end.
Bye. Thank you so much.